All right. So, uh, hi everyone. Uh, okay, you guys hear me? I think the mic is not that great. Huh? Oh, okay. Thanks. Hello. Or maybe I just need to talk closer. Yeah, that works. All right. Hi, I'm Ekapon. So for the rest of the course, it will be me, rather than Ajahn Mili, who took good care of you in the first half, right? I'm sure you have fun with the midterms, right? And I think you saw the projects, right? So yeah, please continue on the project, because that's a big chunk of your grades. But we also now we're starting a new section, which is about machine learning, or what Professor Millie described as like sub-symbolic AI, right? All right. So first, so this is the schedule. So we will have around 8 lectures on this topic, and there will be homeworks every week, but the homework is optional, so you don't have to turn it in or anything. At the beginning of, well, I'll just go here, right? Quizzes. So notice like every every week there's quiz, right? Except for this one, right? Every week there will be a quiz at the start of the class, right? Maybe the first 10 minutes or so. And it's more like, it's not serious. Like you don't have to be worried too much about it. This is just so that people show up on time, or like, actually this part, I won't be as strict as Professor Miri, like as in like, if you don't want to show up, fine, whatever, I don't care. So if you notice, I have this Zoom set up. So every class, there will be a Zoom on my course view. Uh, on my course view here, you'll notice this online meetings, which you also notice this one, right? Which you can just join online. And you can also access the recording online as well from here. So every week there will be a new one every week here. So that's right. So everything is hybrid in this second half, right? So the quiz, you can just, I don't know, if you don't want to attend, just be sure to attend the first 10 minutes. The first 10 minutes. Right. And might as well stay for the rest, right? If you attend the first 10 minutes. But you can also do it online as well. So yeah, and it's an open world quiz. That is, feel free to collaborate as AI or whatever, right? Since we are taking an AI course, might as well, why prohibit you from using AI, right? Last year, the quiz, like last year, the quiz is a little bit too hard for the AI to answer correctly, but I think 1 year later, the quiz should be, like any AI model should be able to answer the quiz by now, right? So that's the quiz, right? Every week, just be sure to be here or be online or whatever, right? Homeworks every week, there are homework assignments, right? They are optional, used for like review of materials, and also used for review of the final exam, which will be pen and paper final exam. Books, there's actually no recommended books. Actually, there's one book for the first 4 lectures of the course, but for the deep learning parts, I don't think there are any good ones. So we actually have this as well. So if you notice in my course view in the lecture slides, second half, there's the slides here, and every week I will also provide like lecture notes, which is like a summary, and sometimes there's some optional material that you can read. So here I mark as optional, something like that. So if you're curious to learn more, you can look at the lecture notes as well. For how this course would be great, right? So this second half is 50%, right? There are 7 quizzes for a total of 15. So technically, you can miss 1 or 2, right? Well, you can miss 1, right? You can miss 1, so and you can still get full points, right? Point will be capped at 15. And the final exam is 35%. All right, so this and Ajahn Mili's half will be combined into a total grade of something like this, right? 85, 80, 75, blah, blah, blah. All right.
It's in my course bill, it's just me.
There's a cost syllabus in my course bill. Here. Interesting. Okay. I will fix that. I will change it to 85. This is official. All right, and getting help, right? So you can always ask the TA in Discord, right? And we also provide this AI tutor, which is fun. So in my course view, if you look at the announcement, where is it? Interesting. Okay, it's gone. Maybe. All right. Yeah, when I was like updating my course view, it went down for a bit, maybe because of like AWS and the Middle East. Uh, Right. So if you go to this link, right? If you go to this link, you'll notice this chat interface, which is pretty much just generative AI in the back end with the course material already upload into this generative AI. So you can ask anything about this second half of the course, and hopefully it will be able to answer. For example, if I ask, all right, blah, blah, blah. All right, okay. Right. So you answer things and it will give you the source and the page so that you can look. Right. So that's this, and you can ask in Thai or in English. It's fine. Note that I will also monitor this chat as in and I have access to all the logs. So this is the UI. Oh, somebody already asked. But I can look at the chat log, right? But what I only see is anonymized, right? So I won't know who you are, but I will always monitor this a little bit and see like what are the things that students aren't sure about, right? But feel free to use this and have fun. Hello, hello. ได้ไหมต้องทำยังไงมีผมว่ามันต้องใกล้มากๆเลย
มันใกล้เกินไปอาจารย์
อ๋อ
ไม่ได้จะต้อง
ใช่
หรืออะไรขนาดนั้น
แต่ว่ามันต้องใกล้มากๆไม่งั้นผมจะเสียงมันไม่เข้า ไมค์มันเซนซิทีฟเลยเกินมาไม่พอเฮ้ยได้โอเค thank you
แต่มัน
right we're cool on the logistics right we're cool right if you're unsure ask the tutor maybe he can answer your questions I don't know but I'll be monitoring them all right all right so let's talk about the topic of today which is machine learning so what's machine learning so in short, it's about a field where we try to learn from data. And so in the first half of the course, we talk about symbolic AI, or some people call it rule-based AI, where you try to put in like your knowledge of the world to create like prologue, like programs, right? To program your AI to do something for you. In machine learning, we're trying to move away from that, and we try to use data to automatically do that. So we usually divide machine learning into 3 ways of learning, right? Three modes of learning, which we will talk in this course, right? Which are supervised learning, unsupervised learning, and reinforcement learning. Today, we'll mostly talk about an example of supervised learning. So, but before we go into like learning, right? Let's talk about rule-based, right? Or like symbolic AI. So let's say I have this problem, right? Which is a 7-segment display. So I have this clock thing, right? Digital clock, where I want to identify the number given the input, which is, so this 7-segment, which is A, B, C, D, E, F, G, right? So this is 7 binary values. So it's either 0 or 1, right? So given this input of A to G, I want to write a function that returns the number that is being shown, right? So I can kind of create like a table, right, that describes all the possibilities, right? And then I can write a program, right? A program in Python, or you can do in Prolog or whatever, right? To get your function, which is fine, right? Which is fine. And you did that in the first half of this course, right? But in machine learning, we want to do something different, right? So we want to do we want to we want to learn from data, right? So in order to do that, we need to define the input, the output, and the task that we want to do, right? For example, let's talk about handwritten digit recognition. So you're given an image, right? So this is an image of digits, right? 0, 1, 2, 3, right? So now you need to write a program that turn this image into numbers, right? 0 to 9, right? So if you want to write Prolog for this, I don't think it's well, it's possible, but not pretty. It won't be pretty at all if you want to write Prolog for this, right? So we want to do something different, right? We want to say, okay, we want to find this function automatically from data, right? You want to learn this automatically from data. So what you're going to do is you're going to define a training set, right? Which is an input and output pairs of X and Y, where X is your input. So in this case, it's your image, right? Your image, and you want to output the number, right? So that's your Y, right? This is your training set, and you're going to learn, right? You're going to use this, right? This training set to learn a classifier F, right? You want to use this to learn a classifier F that you can input in new things, right? So you have a new image, you can use this function F to give you new answers. And the process of specifying Y for each X, sometimes we call it labeling, which is usually a manual process, right? So instead of trying to come up with logics or Prolog programs, we use human labor to do this labeling process instead, right? And this kind of framing of having X and Y is called supervised learning, right? So this is the first type of machine learning we're going to learn about, where we are going to learn the model from the pairs of X, Y. And as we go along, we're going to reduce this requirement from okay, we have X, Y, right? What if we don't have Y? Can we still learn something? And what if we don't have anything at all? Can we still learn something, right? But for now, we're going to start with the first one, right? The first one. All right, so what's a typical machine learning workflow? And so we're going to start with a feature extraction, which is getting the X, and then we're going to do modeling, which is finding this function F, and then we're going to evaluate, right? So this is usually the 3-step process. So let's go over them one by one. So, well, first, before we get this X, right, we have to think about what kind of tasks we're going to do, right? For example, let's say if I want to like count people in this room, right? What kind of information I can use? Well, one way is to use a camera. Some people might say, oh, maybe I can use like heat sensors or something, right? A heat sensor, or like maybe measure the noise level in this room, things like that. Right. So there are many kind of inputs for a given task that you can use. Right. So thinking about what kind of inputs and outputs that you want to use, right, is something to keep in mind. And I think like as long as you create this extraction process of like, okay, finding the inputs for your tasks, right? You can build anything usually, right? Nowadays with data. So let's look at, have anyone like watched like Silicon Valley, the series? Two, it's kind of old series by now, I think. It's popular like 10 years ago. So I think like for now it's like not so popular anymore. But let's look at a clip. Let's look at a clip from this series. I wonder if the noise, the video, oh, the sound won't come out because I'm sharing.
God. What will you say if I told you there is an app on the market?
We're past that part. Just demo it.
Okay. Let's start with a hot dog.
Binyang, my beautiful little Asiatic friend, I'm going to buy you the palapa of your life. We will have 12 posts, braided palm leaves. You'll never feel exposed again.
I'm gonna be rich. Fuck you, Guilfoyle. Do pizza.
Let's do pizza.
Yeah.
Pizza.
Hey, Zach.
Yeah, sure. Yeah, I think it's a little bit too bright.
Not hot dog.
Wait, what the fuck?
That's it. It only does hot dogs.
No, and a not hot dog.
Give me that. Ditch me.
Still quite dark.
Binyang, motherfucked. I gave you the ability to spin gold. Instead, you spun pubic hair with shit in it and
Right. Well, I think that's all. Yeah, you can turn the lights back. I guess this projector is not so great anymore. But anyway, right, so that from that, right, you can have like many kind of ideas, right? So in that video, they do like a hot dog and not hot dog classifier from image, right? You take an image and then it will tell you whether it's a hot dog or not a hot dog, right? So from that simple example, right, how can we train something like that, right? So what you're going to do is you're going to say, okay, you're going to take lots of images, right? Whether it's like hot dog or like a boot or anything, and you're going to label it, right? Label it as, okay, this is a hot dog, this is not a hot dog, right? Take a lot of images and then use this as a training set and pass it through some learning algorithm to give you some model, right, or some function. In this case, it's h that you can use for any application. Right? So in this thing, right, since from the example of this hot dog, not hot dog, right? So since we're taking images, how do we pass this into the learning algorithm? So usually here, we're going to use like mathematics, right? So we have to convert our input into numbers. So we have to digitalize our inputs into numbers for the computer to do, right? So in this case, since the input is an image, you can turn into a digital image and then pass it to the input. What if it's something else? Let's say temperature data, right? Temperature data, you still have to turn this, digitalize it into some numbers and pass it to the model as well, right? So here, the key here is that you need some process. You need some process that will turn your inputs into some set of numbers so that your model can decide on, right? So this can really depends on like your application. For example, if I want to predict the weather tomorrow, right? What kind of inputs should I use if I want to predict the weather tomorrow? Anyone just shout out? Temperature? Okay. Huh? Humidity? Anything else for weather tomorrow? Huh? Wind speed? So satellite image, right? Historic. Okay, let's say like past 7 days, right? Past 7 days, right? What else? Yeah, that's cool, right? Animal behavior. Interesting, actually. But let's discuss just this, right? So this is trivial in terms of like turning into numbers, right? Humidity also trivial. Wind speed. You might need direction, right? Direction as well, and the velocity, right? So that's okay. Satellite is an image. Past 7 days, right? You can also just keep track of the numbers, but how do you turn animal behaviors into numbers? The position. Yeah, maybe you can like, I don't know, put some GPS on like birds or something. Sure. But yeah, like this is just more like an exercise, right? That okay, for different things you want to input in, right? You have to be quite creative. Or let's say, okay, I want to predict. Okay, let's talk about something current, right? The oil price. The oil price tomorrow. What would you do? Yeah, oil price for like the next 1 month, maybe. Yeah, okay. Insurance rate. Yeah, consumption. But like, what about like how would you put in like the war situation into the model?
Should come, when a ship comes up if the water goes higher.
Sure. Yeah. Well, nowadays the insurance company just stopped issuing insurance, I think.
But hopefully, you get more money. It be less boat. It's gonna be boats.
Sure. Yeah.
Probably measure the amount of boats coming in and out.
Yep. So actually, there's like some companies that look at satellite image and like counts boats in like in the dock and see like how busy they are to do this kind of things. Right. So what they do is like take satellite image and then count boats. Right. What else? What else? You're missing the most crucial factor. It starts with a T. All right. What's the most crucial factor now? Huh? Yeah. Well, yeah, satellite image usually measure the price, the situation now, right? But for future directions, oil price. Yeah. Yeah. Hmm? What? Taxes? Tax rates? Maybe, yeah, yes. Yes, pizza index, right? Pizza index. But you're missing the most important one, which is like Trump tweets. You need to follow his tweets. Right, because like for example, like he say, oh, we're going to help insure the boats and things like that, and then things stabilize for a bit early this late night today. All right, so but yeah, that's just some examples, right? But something to keep in mind is that when we're thinking about like things to put in the model, right, we need to really think about the effectiveness of this kind of like inputs. And there's a saying in machine learning that if you have garbage in, you will get garbage out. That is like if you have bad data, even though you have like a perfect model, you can have bad results. Or if you have a garbage model, you can also have bad results as well. Right. And an important thing that we won't talk much in this course, but I think it will actually affect more of your model performance is like data cleaning, right? So this is an example of a cartoon. I'm not sure if you can read from the screen, right? But it's about a boy that is messing up the data of some poll. Right? So here it's like, oh, I'm filling out a reader survey. And he said, okay, how much I spent on gum, $500. My age, 43. Favorite flavor is garlic curry. Right, so this person just answer like random things, right? And then he said like, oh, this magazine should have some amusing ads soon. that is like, oh, if you work on this data, you work on this data, you get bad results, right? And you will work on bad outcomes. And another important aspect, right, that we won't discuss much, but I think it's very important. So we'll talk about it now. Is the evaluations of models, and I think it's getting more and more important as we are more into like generative AIs. That is like, how do we evaluate models, right? Because nowadays, right, when we want to pick a model, let's say, so a lot of people always ask me like, should I use Claude? Should I use Gemini? Should I use ChatGPT? Right? Which one is the best? Right? Have you ever think about that? Like, oh, which one should I use? Or you just use like, oh, whatever's free. Whatever's free, I'll just use it. Right? But when like people start paying, right? People start asking questions like, oh, which one? If I have to pay one, right? Which one should I pay for? Right? So that's where like evaluations become very important. Right. So usually when we talk about evaluations, we usually talk about measuring failures or errors, or measuring success or accuracy, right? And these things are usually like pretty much interchangeable, right? For at first glance, at least, like interchangeable at first glance, like error or accuracy, they're the same, right? You say, oh, if I have like 10% error, I have 90% accuracy, right? Yeah, they're pretty much interchangeable. But actually, in practice, they're slightly different. When you actually talk to like non-technical people, usually it's easier to discuss accuracy, right? I don't know, when try talking to like your non-technical friend, right? Oh, I have built this machine learning model. I have like 10% error, right? I think they will be able to relate it to you more when you talk about like 90% accuracy, right? That's what usually people, non-technical people or like business people will look for. They look for accuracy numbers. But so like when you want to communicate to other people, I would recommend using like this side of the metrics, accuracy metrics. But I think for as like model developers, people who like create models, I think it's better to go for this side of the equation, right? Because when we improve models, right, we usually improve based on the errors, right? So you're like, okay, I look at the error of the models and then I try to fix it. I can go from like 10% to 9%, right? It means that, oh, this is a 10% relative improvement, right? So this is 10% relative, right? Because when we are like fixing stuff, we're fixing the errors. We are not fixing the accuracy, right? So it's to guide your development. I think it's better to look on the error side. But when you communicating to other people, it's easier to communicate on the accuracy side, right? So this is something to keep in mind, right? When you're looking at this, like try to look from the error perspective, and I think it's give you a nice moral boost as well. When you talk about, oh, I changed my model, I go from 90% accuracy to 91 accuracy, right? It sounds quite lame, right? Oh, you improved by 1%, right? But if you go from the other side, oh, it looks like a big improvement, right? So this is something to keep in mind. And another thing is that in many cases, these metrics aren't that trivial. For example, let's say that I want to trade stocks. I want to trade stocks. So I have a model, right, that predict the stock price tomorrow, right? Predicts price tomorrow, right? How should I measure the performance for this one? So one way, okay. Yeah, moving average. Okay, so pretty much like so the difference, like you say, like the error of the prediction over time, right? Over time. So that's one way. Any other ways? So let's say that my stock price is 100 and I predict 110, and my stock price is 10 and I predict 20. If I use like your technique, which is like, okay, compute the error, both of these has an error of 10, right? But which one is more preferable? The top one, right? The top one, because it's 10%, right? But this one is like you're off by 100%. So maybe you want to quantify your error in terms of percentage based on like the previous stock price. That's another way, right? What else? Yes, a ratio, as in like the percentage. Yeah, okay. What other ways? Maybe sometimes, let's say anyone like trade stocks here. Yeah. Trends. Yeah, yes. So yeah, so you're saying, oh, am I predicting the correct direction, right? Buy or sell? Yes, that's what I'm. So whether you should buy more, whether you should sell or you should hold, right? So that's another way, right? So predicting that, yeah. I cannot hear. Can you speak louder? Oh, confusion matrix. Yeah, so that's the trend as well. Like that is it, like going up, going down, right? But you're breaking it down into categories, right? So that's nice that you bring it up. We'll talk about it more. Yes.
Trading sessions.
Yep, opening and closing price. Yes. So you want to pretty much normalize by like the volatility of the stock, right? Yep. That's another consideration for the metrics as well, right? So you can always like make your metrics more elaborate, and so that it fits more into your application, right? I think that's the main takeaway from this. Another thing besides like what you're measuring is that how you measure the target, right? How do you like specify what's the actual answer you're aiming for, or sometimes we call it ground truths or something that you want to compare against. So this is quite important nowadays, because nowadays we have a lot of like generative tasks where you output sentences or like output images, right? How do you measure whether your sentence is good or not, right? Or here is an example of like a machine translation task where you translate ไปไหน to like two different translation which is equally correct, just slightly different, right? So how do you do this, right? And we'll discuss more when we talk about generative AI on this topic. How do you like measure performance when there are multiple ways to measure? Yeah, that's one way. Yes. So you can have multiple ground truths, right, at the same time, right? Or here. So this are slides from Andre Carpati. He used to be the chief AI engineer at Tesla, and he supervised all the self-driving effort in Tesla like 5 years ago, right? And he discussed about like even simple tasks like labeling the speed limit from a sign can be hard. So because like in different countries there will be slightly different signs, right? Or sometimes your sign can have interesting things, right? Right, or here, right? These are some signs. How would you label this? So this is in miles per hour. So you can label this as 9, 1, slash and 2, right? Or you can label this as 9.5, right? But if you, depending on how you label, right, you're pretty much enforcing how the model will learn, right? Because if you look at just like the surface form, right, how it's written, right, you should expect the model should map to this, right? If you just look at how it's written, but if you want to use this, you cannot use this number, right? You cannot use this number, right? So this is not no longer like a simple OCR, right? Not just like, oh, looking at characters and then outputting something, right? But this is like, oh, you actually have to understand what's being written as well, right? Or here, right? This is a crossing. Actually, this is in Pittsburgh, and there's this interesting sign of like school days only, and these specific times that this speed limit is imposed, right? Which corresponds to like where when the time when like students like change the rooms, right? So they cross during these times. Right, so this the speed limit, or here, right? Simple things like line labelings, right? The lane labelings looks very straightforward, but sometimes you have interesting things in the real world, right? Or in Bangkok, you notice very frequently, sometimes like the lane just disappear. There's no line at all, or like old lines and new lines just happen to be at the same time, and Thai people know what to expect, right? But this happens everywhere, right? Even in the US, right? Or traffic lights, right? Traffic lights. So this is in San Francisco. It's like an art piece. Or here, like the same location, just 1 year apart, right? And the sign got updated to be slightly different, right? The traffic light got updated to be slightly different. So here, there used to be this, right? And now it's gone and it becomes here, right? But humans, we kind of like, oh, understand, right? When we look, but when we're like trying to measure AIs, we have to like label, right? How do we make sure that the models can adapt and things like that? So yes, sometimes in real life, it's not so straightforward. Another thing, and I think one of you mentioned this before, that you can have multiple metrics at the same time. For example, here in, let's say, Amazon website or Shopee or Lazada, there's like a recommendation engine, right? Where you recommend some items for the user. And you can like, maybe you can measure for like clicks, right? Or you can measure for buys, right? Buy volume, right? Then or you can measure for like revenue, or you can measure for profit, right? You can measure different things on your recommendation engine, right? But each of this has different trade-offs. If you measure clicks, you get a lot of, usually you get more clicks than like people actually buying stuff, right? So you get a lot more signals, or you get a lot more data if you're measuring on clicks rather than on like conversion. So there's a trade-off between like frequency of like your learning signal and the business value that you get, right? If you want to like take like business value, you look for the bottom line, which is the profit. But usually that's harder to come. So like in places like Amazon, what they do is that they use a combination of like several metrics. Like they do some weighted combination of these matrices into like a single matrix to keep track of like what's happening in their website. Another thing to consider is like usually in a system, let's say that I have a system where I do speech to speech translation. So I speak in Japanese and I output in English. right, in speech. And one way to deal with this is that you turn the Japanese speech into text, Japanese text. You turn the Japanese text into English text, and then you turn the English text into English speech, right? So there are 3 models: model 1, model 2, model 3, right? And these work in a cascade manner, right? So you might want to measure at each step along the way, right? So that's one way to measure, right? But my recommendation is that besides just measuring each step, be sure to measure at the end as well that, oh, how much effect does an error, let's say, oh, I have an error of 2% here, right? But maybe an error of 2% here will become 0% here if your machine translation model can recover from the error, right? So some error might not be that important in a cascade model. Some error might be very important, some not so much, right? So it's always good to measure at like the downstream performance. All right, so now let's look at some commonly used metrics. So people usually use like these, like error, accuracy, right? And then there's these as well: precision, true positive, recall, false alarm, F-score. So what we're going to talk about in measuring this kind of errors, we're going to look into just one kind of problem, which is something we call a detection problem, right? So a detection problem is a binary classification. So it's only yes or no, right? Yes or no, right? So binary answer only. So like this hot dog detector, that is like hot dog or not hot dog, is a detection problem as well. So in this case, if we look at detection problem, we have 4 possibilities, or where your friend talk about like confusion matrix, right? So this is like the 4 possibilities in your detection problem, where you discuss about the actual, what's happening, and whether your detector can answer correctly or not, right? Whether, oh, if there's something is happening and your detector detects it, right? You call it a true positive. If your detector doesn't detect it, we call it a false negative, right? Or a type 2 error. If there's nothing happen and you say something happened, we call it false alarm. And there's a true negative for the correct answer in this case, right? So notice how when we talk about positive or negative, right? Positive or negative, we usually talk about the detection, right? Detector is yes or no, is about positive or negative. And whether it's true or not, depends on whether it's correct. So, but before we go further, let me ask you something, right? So when I say like, when I say like yes or no here, or like binary of 0 and 1, right? Binary of 0 and 1. How do you assign which one is yes, which one is no? I think this is something that people often like don't discuss about. Let's say that I have like a fire alarm, fire detector. If it's a fire and no fire, which one should be 1, which one should be 0? Or if I have like a cancer, X-ray cancer model. So predict from like X-ray image, say whether the patient has cancer or not, right? Should I say cancer or normal? Should it be which one should be 0, which one should be 1? Is there like a difference whether which one you pick, or is there a difference, or there's no difference, you can pick anything? Hmm. So yeah, that's your friend say cancer is 1, normal is 0. Why? Mm-hmm.
Like it's not, no, I'm not sure. But in this case, you wanted to find cancer, no, if there's cancer, it should return positive, and if not, good.
Okay. So that's one. So your friend say, oh, cancer is something you want to find. So something you want to find, you should make it positive. Sure. Yeah, makes sense. What about I have like a like a quality control camera. So let's say I have like a factory. I have a factory and I'm producing, I don't know, iPhones. Right. And I have a camera that look at the iPhones, right? And say whether this iPhone is okay or not okay. Which one should be positive? Which one should be negative? So okay means, oh, this iPhone passed the inspection, I can use it. This iPhone doesn't pass the inspection, I should throw away. Which one should be positive? Which one should be negative? But if we go with what your friend said before, the thing that you want to find is positive, you go with this, right? Not okay, it's positive. So that's one criterion. I think that's the criterion that people use, right? So class 1 or the positive class is something that you want to find, something that is rare, or something that you don't want to miss. Why? Your friend mentioned that it doesn't matter, but actually it matters. Because why it matters is because when we're measuring performance, we usually talk about we usually talk about recall and precision. And these two metrics specifically looks at the positive class. Right. So what you specify as a positive class matters. And when we were discussing like recall and precision, right? And how we calculate this is like this, right? I think you already learned about this in data science, right? So recall is the true positive divided by the total positive class, right? Or false alarm is this, right? So there's different metrics, right? And different way people, different terminologies that people use. So let's talk about an example. Let's say that you're Google, right? So you're doing web search, right? And you perform a search query, right? Let's say I search for iPhone review, right? I search for iPhone review. What does a recall of 50% means in a web search context? So let's say that, oh, there are, I don't know, like 1 million websites, right? And maybe there are 10 iPhone reviews out there from this 1 million websites. What does a recall 50% mean? Yeah, it means that, oh, in your search, right? In your search, there's five iPhone reviews that is contained in here, right? What about precision of 50%? Let's say that, oh, I return eight websites. Yes, from these 8 websites, 4 of them is iPhone reviews, right? So, well, let's discuss this a little bit. Like in a web search context, do you want high recall or do you want high precision? So you're will you read at every will you read every reviews? I think there are like probably 10,000 phone reviews out there. So I think for web search, since pretty much I think there's like infinite iPhone review websites, right? And you probably won't have time to look at them anyway. Nowadays, I think it's more reasonable for at least for web search, to focus on precision. That is like, oh, if you look at the top few, top field of the results, right? You expect that this top field will be correct, right? So you care more about precision. And usually we call it precision at K. Where, you look at the top K results and calculate the precision of the top K results. Let's look at some more examples. What about I have like a initial screening for cancer? Do I want higher precision or higher recall? Since this is a screening, I might want recall, right? Because I don't want to rule out people at the start. Here, your iPhone face recognition, high precision, right? You don't want people to unlock your phone, right? And if, I don't know, if you're like wearing some mask, right? You can try to take it out, right? You can adapt yourself to unlock it again, right? So I think it's more important to have high precision. What about this last one? Recall. Any other comments? Let's say that, actually, if you look at like social media and you look at some, I don't know, hashtag in Twitter for like suicide, you probably have like infinite amount of hashtag. Maybe not a good idea.
Like even you can search like, oh, what happened to this guy in a broad subject.
Mm.
That's like it's so easy to see on the so it's more than
You mean like from the service provider part, right? What if you're like the government? You're the government. Yes. Yeah. So like, let's say if you're YouTube or like your Instagram, right? And you're detecting like the user has some keywords, you might want high recall, and you can like output some disclaimer thing so that you don't get sued. But if you're the government, right, and you actually have to take action, right, you might want precision. Or actually, in this case, you might want just like a ranked list, right? A ranked list that you just keep going down this ranked list, right? When you have like someone free, that person can look at this top of the list, right? And keep track of this list instead, right? So there are many ways to look at a problem, right? Another metrics that people use is F1 score. Or like F measure, right? Which the equation is like this, right? A lot of people just remember that it's an equation. But I think the one thing that you should remember that is F score is a harmonic mean between precision and recall. Right, so it's an average of precision and recall. And I think it's a good intuition to have that this is just an average value. Because if we come back to here, right, we have some sense of like, oh, what does a recall mean? Right? A recall means that, oh, you can find this much things, right? You can find this much things, right? Precision means that, oh, you can like you can be sure how many things are correct, right? But what does it mean to average these two things? Right? If just coming back to like the definition of precision and recall, what does it mean to average these two things from the intuitive point of view, right? Yeah, so it's just some so my point here is that so yes, it's a quality of the model in a sense, right? But when you combine precision and recall, you lose all the nice intuitive meanings of the two, right? You say, oh, recall is something that you can, how much of the things you want, you get. Right? Precision is how accurate you are in making predictions. But when you combine them, you like get some, average of something, right? You cannot, so you're saying, oh, I have 5 orange, I have 3 apples. I average them. I get 4 fruits, right? You lose some meaning, right? You get 4 fruits, right? So in general, I don't recommend looking at F1 at all, despite it being commonly used everywhere, right? It's more like a thing that people use for convenience to report just one number. But like I said, you cannot really combine two things that mean different things. And finally, right, we talk about the training data, right, how we label it, how we're going to measure the performance. And finally, we talk about some data that we will measure the performance on, which we call the test set, right? And usually when we compute the error, we will compute on the test set. But actually, sometimes we can also compute the accuracy or the error on the training data as well. And this can give you some information about how the model is behaving. And we will talk more about using this and this together later on. There are other things that you might want to consider as well. But this, for example, how much time it takes to train, how much time it takes to inference, right? The memory that you need to run it on, whether it's parallelizable, the speed or latency of your model, right? So that's a bunch of things that you might want to consider on top of the accuracy, right? But this is beyond the scope of this course. All right, we're going to take a break, let's say 10 minutes, but before we take a break, any questions so far? Right, should be quite simple so far. All right, so let's take a break and we'll be back when 10 minutes, right? So we will be back to 2:35. maxima 1 แผ่นอ่ะ
Thank you.
อืมทำไมอ่ะ
ไม่คือเนี่ย
ใช่ใช่ใช่
ไอ้จุฬาใหญ่คือ
อ๋อไอ้ติวเตอร์ใช่ไหมติวเตอร์เป็นแค่ specialized version ของจีนี่เพื่อให้มันเหมาะกับการเรียนการสอนมากขึ้น
มันเป็นแบบใช่
แค่หน้ากากออกมาใช่ใช่ใช่เพราะว่าคือมันออกแบบมาโดยเฉพาะการเรียนการสอน ให้อาจารย์มอนิเตอร์
นี่เป็นงานจาก
ฮะอะไรนะบูลลี่อ๋อ All right. Let's continue. Can you guys take your seats? All right, so we're going to talk about our first model, which is a regression model. So in this part, we're going to work on a task that's just more like a funny task of predicting rainfall amount from the thing this holy cow eats, Paco eats. So we have like a data set of the consumption of this cow for like the exchange students out there. I'm not sure you guys know this holy cow ceremony. So every year we will have a ceremony where we have this sacred cow eats. So we present the cow with different kind of food, and depending on what food this cow eats, we will make a prediction of the amount of rainfall for this year. So before the start of the rainy season, this will happen right around, I think around May or so. This ceremony will take place. So let's say we have this data set of what the cow eats and the amount of rainfall for each year. Okay, so we have this data set, and we want to make a prediction of like, okay, given this year, what's the amount of rainfall? Right. So one way to build this model is to like, okay, let's create a simple model by taking the inputs, right? Taking the inputs and all the inputs. So this is like x1. So we're going to say, okay, this is x11, x12, x13, x14, x15, right? So each of the inputs and multiplied with some parameter theta to get our prediction, right? So this is our model, and notice that this is a linear equation, right? With respect to the inputs. So that's why we call this a linear regression model, where regression in this case means that we're predicting value, right? Predicting some value, some number, right? And linear means that, oh, this equation is a linear, right? And we can write this in a more general form like this, a summation of the theta and x, or we can write it in a vector form, that is, oh, this is a vector theta, and this is a vector of xi, where I here is data point, right? Data point, right? Data point 1, data point 2, data point 3, right? And this j here is feature, right? J is the feature. So this is our notation for our model, right? We're going to use the inputs here to predict the rainfall. Okay, so now how do we pick this theta, right? How do we pick this theta? So, well, if we think about this model, right? Different theta. So let's say I have theta of model A, right? And I have a theta of model B. Each of them will be aligned, right? Each theta will represent by a line. And I might have some training data. I have some training data. So my question then becomes that, oh, if I have the training data, which line will be best for my training data, right? So I need some way to quantify what I mean by like a good fit for this data. So one way to quantify this is to use this function called mean square error, which is we have, so this is, so which is this, so this is our model prediction, right? Model prediction, right? Which is this line here, right? These lines here. The red points are the model prediction, and I'm going to compare it against Y, which is, this is the ground truth, right? The ground truth of each data point. So each data point, I have what the cow eats and the amount rain for that year, right? And my difference here is the error, right? Prediction error. But I'm going to square it. Why, right? Because my error here, if I take the error, right? If I take the error here, I get, let's say I get negative 3, right? This one I get an error of 2. This one I get an error of -1, right? I want to combine all the error together, right? But some of them I overshoot, some of them I undershoot, some of them is positive, some of them is negative. So I square, right? So that I combine different direction, right? Whether I'm positive or negative, I square it so that I can combine them, right? And I combine them by taking the mean, right? So this is the sum and divided by m. So this is the mean. Right. So this gives us the mean square error. That is, oh, we are taking the error, but we are going to average it. But if we just average, they will cancel out if we just average. So we square it so that we can combine them together, right? And this gives us some sense of how bad our prediction is, right? How bad our prediction is. And this function here, we call it the loss function or cost function, right? So this is a common term. Sometimes you will hear objective function. So usually when we talk about objective function, we want to maximize. When we talk about loss function, we want to minimize. So this is a distinction between the two. They're pretty much the same thing, but just different direction in the optimization. Okay, and before we do anything else, we want to minimize, right? We want to minimize this loss function by finding the best zeta, right? Finding the best zeta. And since we want, or in other words, we want to find the arc min of zeta for this equation. And without loss of generality, I can change this equation by multiplying by m over 2. Right, so this equation becomes this, but I still do the same thing, that is arc min zeta, right? Multiplying by m over 2 doesn't change where zeta is minimized, right? Where the optimal zeta is. Okay, so now our goal is to minimize this equation. How do we do this? So if we go back to our calculus days, right? When we have a function and we want to minimize it, what do? We differentiate and we set it to 0, right? So we differentiate. So let's say we have this function, right? We differentiate it, we set it to 0, right? And we solve, right? We solve and we get x equal a, right? And we're, oh, this is our answer, right? So this is one way. This is one way. We call this the analytical solution. The analytical solution. Another way, which is something that used for larger data sets, is what we call the iterative technique called gradient descent. So in gradient descent, what we're going to do is, okay, let's say we have some function, right? So this is function y equal x minus a square that we did before, right? We take the derivative, which is equals to 2x minus 2a, right? So this is our derivative. What does the derivative mean, right? Derivative means rate of change, right? Or it means that, oh, if derivative is positive, what does it mean? Is increase x, y increase, right? If negative, increase x, y decrease. So from this observation, we can do something like this. That is, okay, we want to minimize this. So let's start somewhere. So let's say, oh, I start here. So let's pick some y value. Let's say, oh, x equals minus 3. Right. I will look at the gradient at minus 3, and oh, this gradient is negative. If this gradient is negative and I want to minimize my value, right? I want to minimize my value. What do? I have to increase x, right? So I have to plus x because my gradient is negative. So I will move, right? Let's say, oh, I move a little bit. Now my x equals to negative 1.8. I will go look at my gradient. Oh, the gradient is negative again. So I will move in the positive x again. So I can keep doing this, right? By looking at the gradient and move, and looking at the gradient and move, right? I can keep doing this, right? Even if I over move, like let's say here, right? I'll say gradient is negative, but I overstep, right? I overstep to 4. If I overstep to here, the gradient will be positive. So when I have positive gradient, I will go the other way, right? So I can always just follow the negative of the gradient, right? Gradient is positive, I go negative direction. Gradient is negative, I go positive direction. So I always go opposite of the gradient in order to minimize. So this is what we call gradient descent, right? It's a very simple technique that pretty much powers every technique that you have heard of. I think in data science, class, you probably heard of XGBoost model, right? What does it stand for? Anyone know? It stands for extreme gradient boosting. So the gradient here is the gradient descent. Right. Neural network also use gradient descent as well. So this example is an example in like one dimension. That is, we're changing x, right? We're changing x in order to minimize y. If we have like x1, x2 that we want to minimize y, we can think about this in like as like a map that, we are looking at the gradient in this 3D world, like going down, right? No matter how many dimensions you have, you can always use this technique. Okay, so the formal definition of gradient descent is as follows. You start with some function, right, that you want to minimize. You want to argmin, right, argmin of this function by picking x. So you start with a starting point, x0, and you move along the negative direction. In other words, you say, okay, I am here, n. I change by negative gradient to get a new step, right? n+1, a new step, n+1. And I have this r here. So this r is the learning rate. It determines how far you're stepping, whether you're going to follow, how far you're going to follow the direction. So for example here, if I start here, right, and I have a small r, right, I might just be around here, right, because I cannot move that far and go past this stump. But if I have a large r in this thing, I might be able to walk past the stump if I step far enough. But sometimes, if I have too large, it might overshoot, right, and never comes down as well. So usually, this learning rate is a very important hyperparameter that you need to tweak, and we'll talk more about this as we go along the course. This will be very important in neural networks, but for for now in linear regression, it's not so important. All right, so we're back to here, right? We're back to here. So we want to find, right? We want to find this, right? But what we need is, we need what? We need the, we need to find the gradient, which is dj by d zeta, right? dj by d zeta. But zeta here is what? This is a vector, actually. It's a vector. How do we differentiate a vector? Well, one way is we can do partial derivative. We do it dimension by dimension. So what we're going to do is we're going to take the partial derivative of, okay, I'm just going to write it here so it's easier. Partial derivative of some j. So zeta is a vector, right? A vector of zeta 1, zeta 2, zeta 3, right? So I'm taking the partial derivative of one of them. And let's call that j. And I have my equation here, right? So let's take the derivative. So if I have a partial derivative here, what happens? What do I do first? I'm like, oh, I forgot everything. What do I do first? So what is this summation of? Is summation of I. What is I again? I is data point, right? Data point. So we can move inside, right? Because it's a summation of I, but we're differentiating with respect to j. So this becomes and we're taking derivative of this. How do we take the derivative of this thing? Chain rule. So let's make this explicit. Oh, wait. These are vectors. And we have okay. So we're differentiating this thing next. If I take the derivative of this part, what do I get? 0, because y is not a function of zeta, right? Y is our ground truth, which is given to us. It's fixed. So this is 0. What about this one? This one is summation of k x I k. Right, so this is the dot product, right? So let's say, oh, I'm taking the derivative of zeta 1, let's say. So yeah, anything that is not zeta 1 goes to 0, right? And I only left with theta, I'm only left with fxi1, right? Because theta 1 just disappear, right? Becomes 1, but the rest becomes 0, right? You get this plus 0 plus 0, right? Plus 0, everything else is 0, right? So here, right, you get, so notice this thing cancel out. This is the reason why I multiply by 1/2, so that this can cancel. So that is pretty. And negative xi j. Right, so this is my gradient. Okay, or I write like this. So the notation here is just that the j feature. Right? I write like this just to be very explicit that, oh, I'm taking the j feature. It's the same thing as xij. Right, very straightforward, easy, right? Easier than your calculus course, I think. You guys are cool. All right. Well, I can chat here. So, but this is cool, right? We get our gradient. So which means that we can train our model by initializing theta and then calculating this and then do gradient descent, update theta, calculating this again, update theta, calculating this again, calculate theta, right? Which is cool. Another thing that I want you to look at is, what does this equation imply when we are training the model? So this means that, oh, we're updating the model according to what? This is what? The sum. And we say, what is this? Error, right? Error. And this is what? Size of feature, right? So this is what we're updating against, right? And this sum, what does it mean? It means that, oh, this is, if my error, let's say that I have, my line is like this, my line is like this, and this is my point, and I'm updating the model, what will happen? The model will get pushed down because there are two words, right? Because in the end they get combined, right? Right. In the end they get combined. So that's one thing, right? So this update is pretty much like a combination of voting power, right? But the voting power is not equal in a sense that oh, if I have something like this, I have some data and I have an outlier that is like, oh, some data that is maybe mislabeled or like someone mistyped. What happened? So these guys give you small votes, right? But this vote dominates. So your model will get pushed like this, right? So this model is prone to outliers, right? Because this is how your gradient is calculated. You take the error value as your direction and you sum them, right? So that's one thing about this sum of error term, right? Another interesting point here is this. Your movement depend on the size of the feature. And I talk about this, how large your step, right? How large your step. If your step too small, you might not, no, your model is trained slowly. If you step too large, your model might explode. And your model might explode. But here, this is for one feature, right? And if we go back to this equation here, so here, for each feature, I will have this equation. For each feature, I will have this equation. So I calculate the gradient for each feature. I update the feature, right? But I have the same R. The learning rate is set to be the same for all features. What does it mean? If I have a feature that is large, it might explode. If I have a feature that's small, it might be very slow, right? And I cannot pick something that works both ways, right? So what do people do? Well, that's average. It's picking the worst of both worlds, the worst of both worlds, right? Now, try to think about like what do you usually do when you train a model? Normalize it. You normalize the features, right? Oh, feature that is large, you normalize it to something, right? Feature is small, you normalize it to the same thing. Once you're on the same scale, you can use the same R, right? I think this is something worth pointing out, right? Because I think usually when people talk, oh, when you train a model, you normalize the feature, but nobody tells you why, right? This is one reason why, right? You have the same learning rate and you have this, you want to treat every dimension in the same way, but your feature is of different size, right? So that's another thing. Another interesting point is, well, back to here. So here is so you have the error, right? And you have the size, and you have, this is like the average in a sense, right? And where does this come from? It's come from like differentiating the square. Right? You differentiate the square, you get this. I think in data science course, Ajahn Pirapon told you about mean absolute error. Yes. MAE. Or some people call it L1 loss. This one is MSE. People call it L2 loss. If you differentiate this, what happens? How do you differentiate the depth field value? You're like, oh, how do I differentiate this? Yeah, you can just do two if statements, right? And just trust me that, well, you can think about x squared. What do you get? You get 2x, right? When you have x, what do you get? 1. So when you get here, you get just direction of error and xij. If you differentiate the mean absolute error. So instead of voting with like some scores, you're voting with everybody has the same equal votes. So in the case of outliers that we have before, right, this won't have any effect because this only have one vote, right? So that's why MAE is robust to outliers. Hopefully this like gives some more insights on what you learned before. All right. Last point here is batch. So here in your calculation, you're going to sum all this M here is all data points, right? Which can be large if you have a large data set. Let's say you have 1 million data points. You will sum across 1 million votes, and then you will move one step and do another 1 million sum and move another step. So this can be very slow. So what people do is, let's say you have 1 million data. Oops, here, 1 million data. You're going to split the data into smaller pieces and then just sum and then move, right? So your assumption here is direction of movement of gradients, right, of small batch is approximately the same as the large batch, right? So this is a key assumption here, that when you like, okay, you're going to move with a small set of data, they give the same kind of direction, right? So this kind of technique is called stochastic gradient descent. So the stochastic here means that, oh, you're going to randomize this data, and so there's no guarantee that you get the same direction, but approximately you will get the same direction on a larger scale, right? On a larger scale, you will get the same approximation, but you're not guaranteed, right? And usually when people do this, they will have to divide this by the batch size so that it behaves nicely as well. All right, and I think we talked about this before, like L2 loss, L1 loss, and how L1 loss and L2 loss can, so for example, if I have this outlier, this is an L2 solution, and this is L1 solution, right? So L1 gives you a better line in the case where you have outliers in your data set. Right, and lastly, we talk about linear, right? Linear regression. What about if we want to model something that is nonlinear in general? So one way to do this within the same framework is to consider adding nonlinear features. So here, I just add nonlinear features here, like x squared. You can think of this as just, okay, I have add feature that is clot square, right? And like, oh, this is 16, 25, blah, blah, blah. I just add in more features and everything works the same, right? Everything works the same. But when you start adding nonlinear features, or you can add like, you can make your model curve, right? And as you curve too much, your model becomes overfitting, right? So this is something, hopefully something familiar to you. So that's something to keep in mind, like, oh, how sophisticated you want your model to be, and like the difference between underfitting and overfitting. And lastly, before we talk about predicting numbers, right? We can also do a binary classification. That is, we want to do classification, right? We want to do classification, in this case, binary classification. So how do we do, right? So one way to do is that, okay, we can define y equals 0 if there's no fraud, y equals 1 if it's frauding, right? So just binary class. And we can try to use the same model that, oh, okay, let's do linear regression, right? And predict this y equals 0 and y equals 1. But there's a problem because this equation can give you something, oh, h equals 3.5 or h can equals minus 0.5, right? The number can be higher than 1 or lower than 0, right? And this is kind of a nonsense output, right? So we need some way to scope the output, which is when we use this logistic function where we use this logistic function and we pass it through, we pass our linear. So this is linear regression model through this part is the logistic function. And we get our logistic regression model. Yes. So your friend asked a very interesting question that, oh, if you want to switch the answer to be between 0 and 1, why can't just say, oh, if can we do this, right? The answer is yes. And this is also, this has a name, it's called 0-1 loss. And it's a valid choice. The reason why logistic regression use this is because we will do gradient descent, and this function has a nice gradient compared to this thing, right? This thing, you have some problems here, but yeah, it's still doable with gradient descent, and people can do gradient descent on this, but it's not so nice. And actually, next time we'll discuss more about why this form is preferable, but not this time. But we'll talk more about like what's the meaning behind logistic regression. Because here, well, this is a question that I'll just leave dangling for now, is that if we define the test like this, y equals 0 and y equals 1, fraud and not fraud, right? How do we define the loss function in a differentiable manner as well? Because in the end, we want to differentiate. We can always do mean square error, but mean square error doesn't have like, well, it can work, but can we do better than mean square error? Right? And this is something that we would discuss next time. Right, but just to give you some spoilers. Next time we'll show that the gradient of the logistic regression. So this is the logistic regression gradient. Looks very similar to linear regression, right? All right, so that's all for today. Let me talk a little bit about the homework, which is optional, right? So the homework, oh, I haven't uploaded. I haven't uploaded, but this is the homework. So it's just some simple exercise like, oh, calculating the metrics, blah, 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 right? But then the second part is more, oh, actually, this is wrong. Where is it? I think this is one. Yeah, this is this year version. So calculate the metrics, right? And then this one asks you to do the Titanic data set. I'm not sure if any of you did the Titanic data set before. It's a data set about like Jack and Rose, right? Whether a passenger on the Titanic survive or not, right? Yeah, the Titanic data set, but you're going to implement linear regression using NumPy, writing the update equation, like the gradient descent equation. Like just try writing it in code, just to get a sense of like what's happening. Right. If you get stuck, just ask AI tutor. Right. Just ask AI tutor. And like, well, I haven't uploaded this to AI tutor, but in AI tutor you can ask like, oh, homework 1, question 6, give me some hints. You don't have to upload the question and it will answer for you. So it's quite convenient. Yeah, I haven't uploaded, I forgot. Let me do it now before I forgot. All right, the homework is up. And so you can have fun with it. And don't forget, so that's all for today. If you have questions, feel free to ask now or like ask offline. And don't forget, next class, we start having the quiz, right? The first 10 minutes. Right.